Hi, everyone. My name is Khurram. I'm a research assistant at the RLA lab, and I'm going to talk about some of the work that I've been doing over the past few months. So this work is a really large body of work. I'm going to present one slice of it, and there are many people working on it, especially Hasib Shah, David Tao, Rich, and Martha. So let me just give you a brief roadmap for the talk. There are two different parts of this. First, in the first 5 minutes, I'm going to give you a motivation for why I'm interested in this set of solution methods that I'm going to talk about today. And this part is going to be a bit vague and hand-wavy. And then in the second part, I'm going to present one such algorithm which satisfies the constraints that I want to satisfy. And that part would be more concrete. So let's start with the motivation. So my really big goal is to build agents that can operate in large and in ever-changing worlds. And there are two components that I think these agents absolutely must have. One is that they must learn in real time, and the other is that the learning algorithm they use must be scalable. So what do I mean by real-time learning? Well, the agent is interacting with the world. Maybe it's making predictions or taking action. It gets some feedback from the world. Now it can choose to ignore this feedback, or it can store this feedback and use it for learning in future, or it can use it to learn immediately. When I say real-time learning, I mean the agent which uses this feedback to learn immediately. Now, usually when I give this talk, I will try to justify why I think real-time learning is important. But for this audience, I'm going to assume that most people already believe that this is important. And even if you don't, just for the sake of this talk, assume that I'm interested in problems for which this is essential. And the second component that I want to talk about that an agent must have is that it must use a scalable learning algorithm. So what do I mean by a scalable learning algorithm? So let's look at the resources that an agent might use in terms of memory or in terms of operation. Now we can categorize these resources as used for inference or making predictions, or used for learning. And a learning algorithm is scalable if the resources the agent uses for learning are comparable to the resources used for inference, and both of them scale linearly with the number of parameters in the network. Now, why do I think this kind of scalability is important? Well, one is that the world is extremely large, and really the upper limit on the performance you have is because of the size of your function approximator. You would always have to make approximations, and if you can make fewer approximations by increasing, having more features or parameters, you can do better. Second is a more of an empirical observation that people have observed that on large problems, if you increase the size of the network, the performance does improve. So I can show some plots from recent deep learning work. Now, I'm not going to explain the plots in detail, but what they're showing is that for a fixed problem, and a fixed algorithm, if you increase your network or neural network, the performance improves as the size increases. Now, people in deep learning, people call these scaling laws, and it makes intuitive sense because the problem is large and you need to make fewer approximations. And the third reason is that, and this is somewhat of an indirect evidence, that animals have really large brains. And because brains require a lot of energy, we can assume that if these large brains were not beneficial, well, they would have smaller brains. Now, this is really not a very foolproof argument, because we don't really know what's happening in the brain, but let's indulge ourselves. Let's assume that the number of synapses in the brain correspond to a number of parameters. We don't know that's the case, but let's just see what kind of brains animals have compared to our algorithms. So if you plot our existing large-scale algorithms on this line, where the lines correspond to a number of parameters or synapses these systems have, you get something like this. And then if you look at the brains of the animals, you get a very different image. Even very small animals that are not considered very intelligent have very large brains. And when you look at smart animals like mammals or humans, they have a lot of synapses. Now you can argue here that, well, maybe that's not a problem. GPT-3 is already very big. Our computer is increasing exponentially. And then hopefully in the future, we'll get there. But the picture is a bit more dire than this, because if you look at the amount of energy that animals use, or the human brain uses about 20 watts of energy. This is a rough estimate from different sources. And GPT-3, on the other hand, uses a few millions of watts of energy for learning. And this is not just because our hardwares are inefficient. So it's not the case that we can design more efficient hardware to get there. The real reason is because GPT-3, even though the function approximator is very small, the amount of resources is used for learning are much more. So it uses a batch size of about 1 million, which means it's using 1 million times more resources for learning than it is for inference. This is also true for other algorithms. So if you look at, for instance, DQN, 99% of the memory it uses is for the experience replay buffer. I'm talking about the DQN in the 2014 Atari paper. Okay, so that was my 5-minute motivation for why I think we need to develop algorithms that are scalable, so we can really have large function approximators and learn those function approximators online. Oh, one thing I want to mention is that here, if you look at this picture again, if you don't think real-time learning is important, then this is not really a problem, because you can train them once, deploy them, and that's what most of the deep learning community believes in, which is why they're fine with the way things are going. But if you think real-time learning is important, then you have no choice but to learn online, which means your learning algorithm cannot be significantly more expensive. Okay, so that said, now let's jump into one example of an algorithm which satisfies these criteria. So first, I'm going to define something what I call real-time neural networks. So the goal here is that we want computation to be completely distributed and also scalable. Now let's look at a standard neural network. A standard neural network already has fairly distributed computation, but it has one issue that information processing in different layers happens sequentially. So for instance, if you have an input of 5 and you have this simple neural network, then in the first step, you would compute the first node. In the second step, you would compute the value for the second node. And in the third step, you would compute the value for this third layer. So you need 3 sequential processing steps to compute the prediction of the neural network. And that's bad because we want a completely distributed system. So I'm going to define something what I call a real-time neural network, in which every neuron will look at the incoming weights and the incoming values and update its value at every time step. So there is no sequential layer-by-layer processing. So imagine your input stream is 510, then at first time step, 5 would go to the first node here, and then in this next time step, this 5 times 1 will become 1, and 5 times 2, this would become 10. And then the next input, 1 will come here. And in the next time step, 5 times 3 is 15, 1 times 2 is 2, 15 plus 2 is 17. So this value will become 17, and so on and so forth. So if you look at this, information is processing forward 1 time step, and similarly, you can propagate information backward 1 time step, such as gradients, and do backprop in this case. And these networks, once you have them, then you can if you have a good enough parallel hardware, then you can run it and scale it really well. But of course, the question is, how do you train them? And one more thing I'm going to point out is that if you look at this value, this prediction is a function of the observation at time step 1 and 2. So in a way, these real-time networks can also have memory even without recurrence, just because of these delays in these connections. Okay, so I'm going to now present an on-policy prediction learning algorithm that uses these real-time networks. And the initial conditions for these algorithms are that you have input features and you have a node for prediction. And input features are connected to the prediction node using linear weights. So at the beginning, you don't have any other features, and that's it. Now, there are 3 components to this algorithm. One is you're going to construct new features. 2 is you're going to prune existing connections for whatever reason, maybe they're not useful. And 3rd is you're going to prune existing features, which are not useful. Now, in this talk, I'm mainly going to talk about constructing new features. I am going to have one mechanism of pruning, but that mechanism is very naive. It's good enough for this talk, but it's definitely not good enough in the long run. So let me talk about how do you construct new features. So imagine that you have some existing features, x1, x2, x3, and I'm going to select a random subset of them and then connect them to a new feature, x4. And then this feature would have a nonlinearity, for example, rail. And the weights for these features would be randomly sampled from the distribution, and the step sizes would also be something non-zero. And then I'm going to connect this, this new feature to a prediction node, which is going to predict the online TD lambda error. It's not predicting the actual, it's not making the actual prediction, it's predicting the residual error. And this feature would have a weight of either 1 or -1, and I would randomly sample that. And then it would have a step size of 0. So the idea is that we're going to minimize we're going to try to learn to predict the TD lambda error and use that error to learn these incoming weights. So let's make this converted into steps. So step 1, you select a random number of existing features, connect them to a new feature every m steps. Steps 2, you connect this feature to a scalar with to a scalar output, which is your prediction node with a weight 1 or -1. Step 3, you learn incoming weights by predicting the TD lambda error using gradients. And then after some number of time steps, say k number of time steps, we're going to normalize these incoming weights. So the average value of this feature is 1. And then we're going to discard this weight and then connect this to the actual output prediction node. Okay. So that's the feature construction algorithm. And now I have very simple mechanisms for pruning useless things. So synapse pruning or connection pruning, if your connection is above an age, so it's a certain time steps old, then I'm going to look at the product of the expected value of this incoming feature when this feature is non-zero. So maybe this feature is 0 all the time, but whenever it's non-zero, its average value is, let's say, 0.5. And then I'm going to multiply that with this outgoing weight. And if this product is smaller than a certain number, then I'm going to prune that. And that essentially says that if you're contributing less than a certain threshold to your next feature, then we're going to prune you. And then that's how you prune connections, how do you prune features? Well, if a feature has no outgoing connections, then you just get rid of that feature. So pruning mechanism is very local. So let's use this fairly simple algorithm to do some sandwich check. I'm going to test this on an algorithm that requires some memory. So it's called trace conditioning. This is from a paper that Banafshi et al. Recently submitted to arXiv. So, and this is the simplest possible experiment in this paper. So my input feature is just a vector of 2. It has 2 values. The first value is called CS, or conditional stimulus. The second value is called US, or unconditional stimulus. And the goal is to predict the discounted sum of the US. And when CS is 1, that means the US would be 1 after a certain number of time steps. So here I'm saying that if this value is A and B, and this is part of the problem specification, then the US would be on so I would sample a number between A and B, and then US would be on after that number of time steps. And this interval AB is called ISI. And then once US is on, so US is 1, that means the next CS would occur after 80 to 120 time steps. And this is just a way of resetting between episodes without actually making it episodic. So it's a continuing task. And then your gamma is this value where this B is this upper limit here. And basically this gamma says that you between CS and US, you always want to predict something. So your prediction would go up immediately. So what would an example sequence look like? It would look like 1, 0, so CS is 1, and then you get a bunch of inputs that are all 0, and then the US is 0, and you want to predict the discounted sum of this value, and then you get a lot of 0, 0 inputs for 80 to 120 time steps. So if you apply this algorithm on this simple task, it can learn to solve it perfectly. So I'm not going to show you any learning curves, but I am going to show you the network that it learns at the end. So let's look at ISI 4.4, which means that the US happens 4 time step after CS, then there is no stochasticity. Well, the network that it learns, if you have this problem, is something like this. And this is in fact the most compact network you can learn to solve this task. So it has a depth of 4, and that's exactly the amount of memory you need to solve this task, because you want to predict something happen for up to 4 time steps. And it has these skip connections to fill the gap. So your prediction rises as it should if you're trying to predict a discounted value. And then if you apply the same algorithm with a different ISI, so now ISI is stochastic, 14 to 26, then the network that emerges looks very different. But this is also, if you look at the error, this is close to or the optimal solution for this task. And then if you zoom into this network, what you would see is that it uses the US to reset the prediction as it should. So if you see US after, let's say, 16 time step, you would want to make your prediction 0 immediately. We can also try to test if the tester is working. If the network is getting rid of useless things, we can make this test non-stationary. So what I'm going to do now is I'm going to change the ISI from 1426 to 4.4 after a certain number of time steps, and then that will happen periodically. And then I'm going to plot the number of connections this network has as time passes by. What you see here is that as time passes by, the network adds more connections, more features, and then at this point, it's predicting the 1426 case perfectly. And then once the problem changes, it loses all the user's connection and becomes shallow again. And then again, when the problem changes, it becomes deep again. So essentially, the size and the topology of the network is changing as the problem is changing, which shows that the naive tester I talked about works fine for this problem. Now that was a sanity check. Now we can make the problem a bit more complicated. So this is trace patterning. This is from the same paper, but it requires some form of feature learning. So now I have 7 inputs, and the first 6 are the CS, and the last one is again the US. And in the first 6, 3 of them would be 1, 3 of them would be 0, and that leads to a total of 20 possible patterns. And 10 of these patterns would lead to a US and the other 10 would not. So what do I mean by that? So it's possible that if you see this pattern 1, 1, 1, 0, 0, 0, then the US would happen after a certain number of time steps, whereas if you see a different pattern, then US would not happen. So this involves, to solve this task, you have to learn these nonlinear features, which can recognize these to differentiate between the 10 patterns that lead to the US and the other 10 patterns that do not lead to the US. And so this is just an example of what the ideal prediction looked like, followed by the right pattern. So let's look at the actual learning curve here. The agent is minimizing the loss pretty robustly. Now that's good, but also let's look at what kind of prediction it's making, because this doesn't tell us much. So now I'm going to plot for 5 randomly chosen patterns, I'm going to plot the actual prediction. So the pattern in the top, US is not followed by these patterns. So the agent should just predict 0. And the pattern at the bottom, US is followed by these patterns. So the prediction should be something more reasonable. And what you see is that, as you would expect, the prediction is indeed very close to 0 in the first case, and it's much better in the second case, and it looks very nice. Now you see this thing where in the beginning it's predicting some large value for this pattern, and this is something in these networks you would see very commonly. That's because if you want to predict something immediately, you can only use features linearly, because these are real-time networks. And if you want to use a deep feature, then you have to wait a certain number of time steps. So what happens is that in the beginning it makes mistake, but then once it has some deep features, it knows how to do well. The deep features can recognize patterns much better. And then now let's also look at how the network grows over time. So on the y-axis, I'm adding the number of parameters over time, and the network is growing and adding more and more features. But we would expect that once adding more features is no longer useful, it should stop, and that's what happens. So if you learn for a very long time, after a time, the rate at which the network is adding features slows down a lot, because adding features is no longer useful. And then you would also expect that if you try it on a more difficult problem, then it would add more features. And that's exactly what you see. If you try it on an ISI 2040, then the network grows more quickly. Now, we should also do some evaluation studies. So I'm constructing these features using a very specific algorithm by minimizing the residual error. How can we compare it to other methods, for example, random feature construction? So I'm going to compare this to 3 other methods. One is the one I talked about. So you randomly initialize incoming weight and you tune them using gradient. The second is you initialize incoming weights to a fixed value, so no randomness, but you still tune them using gradient. And the third is that you randomly initialize them, but you do not tune them with gradients. So if you look at these 3 methods, what you see is that as long as you're using gradients, the features you add are pretty useful. But if you do random feature generation, then the network learns significantly slower. And I'm not sure if this difference is very meaningful, because I didn't try to do a very elaborate comparison here, but I did try to make random feature generation work by trying different distributions and different schedules. And for all of them, it worked poorly. So at this point, you could have some reasonable objections. One is that, why am I suggesting to use delays for memory? It sounds very limiting. It essentially means that if I want to remember something for 1,000 time step, then I need a network with depth of 1,000 steps, and you would be right. That is a big limit. And then also, when I generate these features, I could pass gradients, all the way back and do deep feature learning. Matt is asking, are there confidence intervals? Yes, there are. These are 95% intervals. Standard error for for these there are no intervals. For the other plots there are, but I did run it for many steps, and it's pretty robust. It's the different, but for the error plot there are. Okay. And the other reason is that learning doesn't really have to be. Yes, there is window averaging. Maybe, actually, I'm not sure. You can check. The learning doesn't have to be shallow so far. So why do I want learning to be shallow? Well, let's go to the next step, where we actually want to have recurrence for memory, because that's definitely a much better way of having recurrence. Now, before I talk about how we would learn this recurrence in a scalable way, because recurrent learning algorithms are somewhat more expensive, let me just give you a brief overview of how recurrent learning is usually done. So imagine that you want to compute the gradient of this there's a recurrent network, and you want to compute the gradient of this prediction, yn, this prediction. You want to compute the gradient of these parameters, theta1, with respect to this prediction. And you could do this by applying chain rule, and the gradient would look something like this. And then you can compute this gradient in two ways. You can either compute it in the direction of time, so starting from t equal 1 to t equal n, and that's called RTRL, or real-time recurrent learning, or you can do it in the opposite direction, starting from n, and that's called backpropagation through time. And both of these algorithms might seem similar, but they make very different trade-offs. So if you look at the characteristics, well, BBDD has to store past activations because you have to wait for the prediction and then do all the computation. The computation also is not uniformly distributed, which is bad. And then the memory requirement depends on the prediction of the span, which is also bad. RTRL is nicer on paper. It doesn't have to store past activation. Grand computation happens over time, and the memory requirement is independent of span, but it's actually intractable in terms of its complexity. And if you want to know why that's the reason, that has to do with the dimension of these matrices. So computing these matrices in one direction is much better than doing it the opposite way. And in fact, the complexity of RTRL is the number of hidden units squared times the number of parameters. Okay, so now let me just go back to this paper. So how are we going to do this? Well, because we are adding one hidden unit at a time, and we have this nice, and once we add a unit, we are no longer changing the features. That means that the complexity of RTRL is not so bad. So H is just one, which means the complexity of RTRL in this case is simply number of parameters. So you need one trace per parameter to construct this recurrent feature over time. And this is not only true for this simple recurrence, this is also true if you add a single GRU shell or an LSTM shell. And if you want to look at the derivation for LSTM or GRU shell, they are in this paper that it's cited in the bottom. And if you look at the update equations, you essentially have to keep one trace, and the update equation for the trace is also pretty simple. And using this, you can essentially apply the same algorithm, but now construct recurrent features. So how does it work? Now, I only finished implementing this recurrent version over Monday, so I didn't have a lot of time to run this on many things, but I did run it on trace patterning, and I also didn't have a lot of time to tune it. So all I did was I took the feed-forward version of the algorithm, only changed the feature constructor, everything else is the same, and I just ran it with the same parameter. And with the same parameter, you can see that it actually learns much faster. And if you look at the number of parameters it's using, it also fewer. So it uses about 3 times fewer parameters to solve the same task, which makes sense because recurrent networks are better for memory than feed-forward network with delayed connection. So that's pretty much it, but I want to end with 2 comments. One is that they are making 2 very nice choices here. One, I'm making new features from randomly selected existing features. I think that's generally a bad idea once you have a lot of features. So you want to do something smarter by keeping track of statistics that which feature leads to useful features. And there was a recent paper on this by John Martin and Joseph called on Frog Eye that I cited below if you want to read on it. And there are other people working on it too. And the testing criteria I use is also pretty naive. We don't really want to know how a feature contributes to the next feature. We want to know how a feature contributes to the prediction and use and prune them based on that. Now that's something I'm working on, other people are working on as well. So that can be done better as well. And that's pretty much it. Now, if you have any questions, I would love to answer them.
So is the number of parameters going to be a problem? For instance, uh, the 1010 USCS problem, it had, I think, 30,000 parameters.
So that's a really good question. I knew someone would ask it. So first I should address the bigger question that, well, the number of computation the algorithm is using is increasing over time, and that's generally bad. But the way I see it is that there is a ceiling, so there's a maximum number of resources you can use, and you can't go over that. So once you hit that, then you can only add features if you remove all features. And until you hit that, it's always okay to use fewer resources because you can just busy bait. But that's not a problem. Now, you said that the number of parameters are large. Well, not exactly. So let's look at what are 20. So let's look at a very simple STM with 30 nodes, 30 by 30. So if it's fully connected, you would have 900 features. Now, if you use back propagation through time with 30 time step, you're using more computation to learn this very small recurrent network than you would be using to learn this much larger recurrent network that I'm using, right? So once you take into account the learning algorithm, it's actually not using a lot of resources, and it's actually using much fewer resources than even very small STMs or GRU networks would use.
I see. Also, this reminded me of the lottery ticket hypothesis that neural networks, they use very few nodes. Do you have any thoughts
Right.
on that?
I have a general thought about that. So my not specifically related to this. So the way I interpret logic figure is that it just means that when you randomly initialize the neural networks, there are some good features, and then you tune them slightly and you do well, and that's what it shows. And generate and test is basically a continual way of doing that, right? So you're saying that I'm not going to have this randomness in the beginning. I'm going to do it continually. So I don't want to just limit myself to how lucky I get in the beginning. And really, Shivansh and Parash, they are working on a continual backdrop paper. I think that paper and that work is really explains why logical hypothesis works. It just shows that in the beginning you have good random features, and if you do continual learning a non-stationary problem, then you also see that those properties go away. I don't know if that was clear.
Thank you.
Khurram, your construction technique, if I understood you correctly, you add a feature, you create this feature, and you connect it up to the output unit, the scalar output predictor. And in that case, it seems like you're only connecting things that are one step away from an actual output. And is that restrictive? Am I correct? And is it a problem?
I'm not sure if I get it. So the new feature can be a function of any of the existing features. But yes, when you add it, then you use it to linearly predict the output prediction. But then you can add new features, which would use this existing feature that I added, and then you can have 2 steps, and then 3 steps, and then 4 steps. But that would happen over time.
I'm just going to ask a follow-up then. Maybe Rich is suggesting, not to put words in your mouth though, that you could generate features that are not just on the edges of everything. Like maybe you could generate them at the beginning or somewhere in the middle. It's natural, I think, to add them at the end, but have you thought about connecting them otherwise?
So they're not, So if you connect them, so let's say that you have a network and you have this network. So maybe I can also clarify what I'm doing here. Then the new feature I add could be a function of any of these. So it could be something like this. This could be the new feature. And then I will only connect it to the output node. So let's say this is the output node. I will only connect to the output node here, right? The problem with connecting this to other nodes is that then you can create a cycle. And then if you create a cycle, then your gradient estimates would not be unbiased. Right now, the way it works is, even in the recurrent case, they're unbiased. But if you accidentally create a cycle, then things can get problematic. And then there is the other issue as well. The other features are fixed, right? Once they are once they have been created. So if I add a new feature and I connect it to this existing feature, then I can change the value of this feature in unpredictable ways. And that feature is not changing. And you're not learning based on that feature, which could create interference and result in arbitrary behavior or unpredictable behavior.
Shouldn't it be easy though to prevent this by just setting this initial weight to 0?
So that wouldn't work because, so imagine that I make a new feature here, I set this weight to 0, but I'm not doing deep learning, which means I'm not going to propagate gradients here and then back. So that wouldn't work.
Right. Okay. Yeah, that's a problem.
So I did have one version, which I guess is reasonable, in which so let me just make this graph, and then this is the output node. So I did try doing that. I would propagate gradient by 1 time step. So gradient from here would go here and then also go here. And then from here it will go here. And then all of the parameters that updated to some degree. That ensures some bias, but then your network is not fixed. But then I compared it to the other version in which I fixed them. The performance is similar on these benchmarks. And I would rather have an unbiased version, at least when I'm working on it in the beginning, because I don't want unpredictable behavior, especially with recurrent networks, which can be jumpy.
This also reminds me of gated linear networks. Have you heard about those?
Which one?
Joel Venice, gated linear networks.
Gated neural networks.
Yeah, GLN. All units try to predict the output, and they're cascaded. All of them are trained in a local fashion. You kind of introduce random weights and like train them from there. But otherwise, the learning really is completely local. There is no backpropagation in the network. They're not growing it, but or pruning, but there are some similarities, I think.
So that I should check it out, and I'll check it out. So from what I've seen, existing work on these generate test methods, most of them don't often learn these hierarchical representations. Some do, like cascade correlation paper does, but most don't. That is one thing I want to do.
What do you mean by a hierarchical representation?
So my new feature should be a function of all, not just the input things I'm getting, it should be a function of other features.
Oh, in the gated linear network, yeah, they are nested, so you have
I
that
see.
for sure.
So I think we should all note this thing that you're doing. You're trying to avoid deep backpropagation. And is that good?
So the goal is to avoid unscalable algorithm. If someone can do deep propagation, keeping it scalable, I'm happy.
Yeah, you see deep backpropagation as being problematic, sort of temporally, because it takes time to compute the output, and then you have to go back, propagate it back, and it'll be late, it'll be out of date. It'll be problematic to do efficiently in a computer. And so one thing you could read out of that is a motivation for doing things like Martha has been doing and her group has been doing on networks of learning agents, which are distributed and which are their feedback is a reinforcement kind of feedback. You know, they do something and then sometime later they're learn that it was good, and that kind of feeding back may be more amenable to being treated in this way. So I guess the clearest example would be if you have utility, each unit can maybe recognize that it's useful because, well, like the output guys are useful, and any of its predecessors that it finds useful, they can determine that because they can know the output guy is listening to them, and then this can propagate backwards. It can propagate slowly, and it could reach an earlier unit and grow a large synapse onto a very early unit, and the feedback can just be the growth of that synapse. So it doesn't have to be like moment by moment gradient variation, like in background. But it can be, oh yeah, someone has found me useful, so I must have done something good recently. Okay, so this is what networks of reinforcement learning units might be able to do, and so it's part of the motivation, I think, for looking at these distributed networks of reinforcement learning units.
Yeah, I think and there are other benefits too, right? You can use binary neurons. That's something I really want to use. That makes testing and everything so much easier. But really, I do have one thing though. I want to be able to learn recurrent features using a reasonably unbiased way or completely unbiased way and a quick way. But yeah, maybe it's possible to do that with the RL methods as well. Martha is saying it's not possible.
Seems hard. I think both of these settings are going to deal with some bias gradients probably. Hey, I have a question. If your depth of your network got pretty large, I guess on each time step, there's like a clock, and things propagate forwards, and also gradients are propagating backwards. So by the time the first node reaches a gradient reaches the first node, it's 100 time steps out of dig. Did you do anything about, like, say, decaying that, or is there any mechanism you can think of that takes that into account?
So that's something that I did. So that's something actually not happening here, right? So I stopped propagating gradients backward too many steps for that reason, but also because for other reasons, because you then cannot learn the current features in a scalable way. If you still want to do that, then in my experience, as long as your step size is small, it's not really a problem, because say it's 100 steps, your parameter wouldn't change so much in 100 steps that the direction of the gradient would change. Maybe it would, but mostly it wouldn't if the step size is small. And then maybe it wouldn't be a problem. So in my experience, scale gradients are not usually a big problem. So I pretend they don't exist. But yes, if the step size gets larger, then they would become a problem.
Can I ask a question?
Mm-hmm.
Did you try to do something like a scaling study when you would have patterns of increasing lengths, and you try to see how the resource use scales with, like the complexity of the task, if you wish?
So there is one that I showed here. Could probably go back to it. So here, the pattern is not changing, but the distance between the pattern and the predicted US
Right.
is changing.
But maybe, yeah, a little bit more comprehensive.
So the only thing I did was I have this pattern-based version, and then I have the first version in which you don't need patterns. Simple, you see one, you predict one. So in that case, the network is very small. It has 40 features, and in this case, the network is very large, 30,000 features. There is definitely difference, but I haven't done a systematic analysis of how it changes.
Right. Because you started to motivate the talk with resource use and whatnot, and with Anima brings the way they're set up and so on and so forth. So I started to wonder, after seeing this huge network, is whether this is like very wasteful and
I actually want to have.
Yeah, okay.
I actually want to have a very, very, very huge network. Like I want to make a network with billions of parameters.
Sure.
What I want to do is that the learning algorithm shouldn't use 100 times more resources. Right? That's the main constraint. So in this case, it is wasteful because I'm fixing some things, and maybe those things are slightly useful, so I won't get rid of them. But maybe there is a more compact representation. That's true. But I would say it's still better to have lots of features if you especially want to predict many things in the future, than to have fewer features and trying to use a much more expensive algorithm, trying to learn a more compact representation.
I guess I'm just worried about that. If on a simple task you need a lot of resources, then maybe the same amount of resources are not going to be sufficient on a reasonably complex task.
So this is how it's a good question. That's a good question. There are two things. One is, so I did talk about that I'm doing a very naive testing here. I think once you have a better tester, like better way of figuring out which features are actually contributing to the prediction, then you can prune more aggressively and you shouldn't really have any wasteful things. And then there is the other thing as well, which is if your features are decorrelated, then this problem kind of goes away. That kind of makes sure that you have a compact representation. So I'm not doing that, but that's also something that I think we would have to do eventually. So we would want to make sure that features are decorrelated, so there is not a lot of wasteful things happening. But still, it looks large, but on the same problem, if you want to use an STM, it uses the same or actually more resources because backpropagation through time is more expensive.
Yeah. I guess it's kind of funny because somehow the way we account for how much resources we use is very different, right? Like if you have this real-time framework, then a lot of things can be free, which are not really free if you have an algorithm like backpropagation through time. So it's like the architecture also dictates what we think is expensive and what we think is cheap, which is fair.
So you're totally right, but actually the opposite is true. So let's talk about backpropagation. Backpropagation, you have a lot of sequential operations. Like the recurrent networks, you cannot do everything in parallel. In this case, everything can happen in parallel, which means if you have a lot of parallel hardware, you can use all of it. You never have to do anything sequentially.
Yeah, I'm saying the same.
So I'm saying it is the opposite, right? It's like backpropagation and LSTMs, they're not as parallelizable, which is why people move to transformers and all that stuff. Whereas these real-time networks are something in which your resources would never be wasted, because you can just it can happen in parallel. And there are these chips, neuromorphic chips that some people are working on. So if your algorithm is something like this, where it's only using local information, then you can actually make hardware which is orders of magnitude more efficient than our existing hardware, because you don't need random access memory, you don't need other things, you only need local information. And that's not true for most other algorithms. So I would say my motivation is to make algorithms for this future chip that they're complete, and they should be completely distributed and local.
This is very funny because in computer science, there is this church Turing thesis or whatnot, which says that the hardware doesn't matter. And what you are saying is that it is the hardware that should be driving everything. And yeah, it's this thesis is not really a theorem or anything like that. It's just like some way of thinking about the problems, but yeah, you're challenging this view. It's fair. It's interesting.
Martha?
I was just going to add the point about being the size of the network growing and then the computation also growing with it. I suppose one way that could not happen is if you had some level of sparsity in the network, or if you always had some number of things active rather than if you just had some number of things active, then you could sort of keep your computation at a similar level, you might think. So, because one of your motivations up front seem to be not to have nice compact networks that are sort of the way we think of it now, but rather to have these big giant networks, and you want the training method to be scalable. So presumably you also want querying those, let's say, to be scalable, and then you would think you need something like sparsity.
So I think in the long run, so we could implement it in a way that it will exploit sparsity. So you have, let's say, 100 processors, and you're feeding information in your process, and it's happening sequentially. But if I look at what's actually possible in the future, it's actually much better to have make hardware systems which are this completely local, and you have no mechanism of, let's say if you have a neuron here, and this is going to be 0 and it's sparse. Well, you don't want to use this processor to compute something else, because the amount of time and resource it would take to get this other information here, is more than if you just don't use it at all. And that's definitely true in let's say the brain. You don't have random access. You can't access random information at random points. And adding that infrastructure is very expensive. So a lot of our computers, they waste a lot of resources in adding that infrastructure. And if you don't add that, then you can make significantly more efficient hardware. Right. So what I'm imagining is that just like a brain, every neuron or every small region has its own local processor. You don't want to transfer information. That's expensive.
So I guess if you want to convince people that this way of thinking is going somewhere, maybe you should also aim for, using some of the existing benchmarks, Amii or whatnot, even though it doesn't look like similar to the task that you were talking about. If you want to convince people that this is the way to go, you should be looking at those benchmarks and get some results which are in ballpark at least close to what is achievable with other ways, or it will be really hard to convince people that it's going to work. So are you planning to do anything like this?
Absolutely. In fact, right now, like I mentioned Steve at the beginning, what he's doing is he's taking an expert DQN agent and doing on-policy prediction for that agent. So not control, but still at least a step up. But I think there are things we have to address, right? So I mentioned there is naive pruning and naive other things. we really have to fix those things before we start doing that. But that's definitely the plan. But that's a 2-year plan, not a 2-month plan.
I wonder whether it would be simpler just to take some supervised learning task first.
So in supervised learning, I would expect it to do fine, but it would. So one thing I haven't mentioned is that all this infrastructure is like, I have my own AutoGrad implemented in C++, but that takes time because otherwise these dynamic inputs are very small. So implementing small things has a large overhead right now. So then I really want to target things which would actually improve the algorithms, at least for now. And then once it's at a place, then I can convince people.
All right. Okay.
But that's a
Thanks.
good point. That should be done.
All right. Thank you.
I wonder, like, did you kind of think about how this network will generalize? Because like, I have this idea that like you show that these networks learn like really efficient architectures for like animal learning environments. But like, it seemed to me that they kind of like overfitted to that environment. So like, do you have any idea, like when you kind of scale it up, like how it generalize? Yeah.
So it's a good question. So let's define generalization in the sense that you're learning something and you want to make, maybe let's learn a new prediction that you're not doing before. And then you would hope that if you have a lot of features, some of them already are useful. And if they're not, then you would make new features. So if the task is similar, the existing feature should be somewhat useful, I would expect. Now, there is this other notion of generalization that people talk about in RL, where you train it on one environment, test it on a different environment by fixing the learning process. I think that's just the wrong direction. So I don't think about that much. Like we shouldn't try to generalize in that way. The agent is always learning. And then if it cannot generalize, it will learn. If it can generalize, good.
So I see, like you're kind of like targeting the continual learning environments specifically, right? Cool.
Exactly. So I skipped part of the talk because I think people here already believe in online learning, but I do think there are two ways of solving this problem, right? You are going to encounter things that you've never seen before. And then in people who believe that you can learn one and then deploy the agent, they really have to solve this out of distribution generalization problem. That you're never going to see it, you still have to do well. If you're in the online learning camp, real-time learning, not really. You'll see something, you'll learn online. So it's less of a problem in my opinion.
Yeah, I agree. Also, like another thing that I guess Marta mentioned earlier was like kind of delayed in the network. So if we kind of consider the continual learning problem and like the network is too deep, like the agent can learn from its observation really late. So maybe I was thinking that because like just consider that like it's like 10,000 time steps takes to like the depth of a network is like 10,000. So it takes like 10,000 time steps to, get a feedback like and learn from it. Yeah, and then the agent, like I think like it takes a lot of time for agent to react to that kind of scenario and learn from it, and it is not good at high risk maybe environment. Yeah.
So that's not exactly true, right? It's like the linear learning always happens instantly. So I would say that if it has to adapt real time, it can always learn the last layer, and then it can learn the second last layer a bit slowly, and then so on and so forth. Right? In fact, now in this case, I'm not even propagating gradient more than 2 steps. But the linear learning part is always happens instantly. There's no delay there.
Yeah, I see.
I had one doubt, suggestion, or comment. Like one thing which I always think about in these things is the aspect of time. Like all this is very not discrete, but it's very similar in some sense that there is an aspect of time, right? But in a stream of so like I'm assuming your method is synchronized by the input stream. The way the rate at which the input stream is coming, your network is behaving at that latency, and that is okay for the things we have right now. But in real time, that does not make sense.
Yeah, no, I totally agree that although we could always implement the clock, but if we didn't have to do it, that would be better. Now, I actually think it wouldn't be a big problem here, right? If your learning is always linear, then I can imagine that you could come up with an algorithm for linear learning in which you can do real-time learning. There is no division between when the time changes. And if you could do that, then you could do the same thing with that algorithm. Right?
But what about having different latencies?
So sure. As long as your latency is predictable, it's fine, right? So imagine you have these two paths. Also, even that's not important. So imagine you have a path from which the latency is unpredictable. The feature would become noisy, and then the output weight would just be smaller, right? Like the linear learner should take care of that. I would expect to take care of that.
Okay.
Yeah, I think that makes sense.
So for a small latency, your variable would tend to become random. You're saying that, right? But yeah, okay.
What I'm saying is that if the last linear learning part, imagine you can come up with a linear learning algorithm that works in the real-time case. Then if you have a path that has very high latency, then that feature is not trustworthy, right? So the linear learning algorithm wouldn't use that feature.
But why would not that be trustworthy?
So imagine that you see something, and then this is the feature, this is output, and this feature after this is on after 1 second or 10 seconds. Let's go to the extreme case. So if you have this much latency, then it's probably not a good idea.
Let's say you have two data streams which are coming from different inputs, and one of the data streams is a different latency than the other input.
That should be fine. I don't think that would be an issue.
Okay.
So backprop requires all this synchronization.
Yeah, backprop is bad in these things. Yeah, you have to
backprop. Yeah, backprop wouldn't work in that. Right. But it could still work. You could still say that I will periodically look at my input. Every 33 milliseconds, I will read my inputs and then process them.
That's the whole problem of finding a good time step for your things. Yeah,
30 FPS. That's good enough.
No, but most games are at 120 FPS. Okay. Cool. Also, you mentioned that the size of the memory is the depth of the network, right? In some sense.
So the memory is the number of parameters, and so that so this algorithm could give you a very wide, shallow network, or it could give you a very deep, non-shallow network, or anything in between, right? So the structure of the network depends on the problem.
So what if you can have a way to kind of summarize a section of the network as a part of the memory, like rather than having each node separately, you find a way to identify which part of the network is acting as a memory, and then basically store that as a hash table or something.
So then you need all these extra wires to store things, random access things, and those wires. Like, my opinion is that you don't want an algorithm that requires those operations.
Have some structure, yeah, but yeah.
So if your algorithm requires that at any node I want to be able to feed any information or read any node at any time in a central place, I think that's too expensive. That wouldn't scale. But again, you don't have to be convinced, right? But I don't think it would scale.
I don't know if this might be too handy. So in a usual brain, the memory is basically a function of the state of the brain, or is there a memory component in the brain then? Because the state of the brain can be as a way to represent memory, right?
Oh, I see what you're saying. So there are two forms of memory you can argue. So there are synapses, weights, connections.
Yes.
That's memory.
Yeah.
And that's permanent. And then there are activations, and both of them are memory, kind of. Like a recurrent feature is a memory, but then the weights are also memory. I would expect that the most long-term memory is in weights. At least that's how I see it. Maybe I'm wrong.
Yeah. Okay.